I know the convincing evidence problems were brutal when we were talking about sampling distribution. Nobody got the convincing evidence problem. All right, I'm sorry. I think that was mostly because we didn't have a procedure. Now we're going to have a procedure for deciding, is there convincing evidence? Why do you use an O for the null hypothesis? It's a 0. So null, I think, is 0. So it's H sub 0, not H sub O. No, 0. Sorry, I had to.
Bazinga!
I had to. It's too good. So, once we have this procedure, I think it'll be much easier to make judgments as to is there convincing evidence or not. We will reinforce what a p-value is. And then the boundary for the p-level is the significance level alpha. Okay. Let's see. I moved the type 1 and type 2 errors into the next unit. We definitely won't, or to the next lesson. So that's what your video will be on for you to take notes on for next time. Those are kind of complicated, not gonna lie. Sorry. There's no getting around it, though. We got to talk about type 1 and type 2 errors. So let's do this. Let's remind ourselves what the heck a hypothesis test is. The basics, okay? So the basics of a hypothesis test. Looking for convincing evidence. First, you have to state and identify the null hypothesis and the alternative hypothesis. All right, so H sub 0, the null hypothesis, that is the original belief. All right, no news here. I think default settings, if that helps, or oftentimes we will use the court system. You are innocent until proven guilty. All right. Like the Volkswagen question that we all love and adore, right? Volkswagen says this is how much emissions their Jetta has. That's their claim. That's your null hypothesis, the original belief. Okay? Then, the alternative hypothesis. All right, H sub A, we just would read this, the alternative hypothesis. You wouldn't have to say H sub A, just say alternative hypothesis. You are looking for evidence for the contrary. You're looking for evidence for something different. All right, you are looking for evidence to show if they are guilty or not. Okay, you are innocent until proven guilty. So we look for evidence to prove the guilty. So the first thing we got to be able to do if we're going to find convincing evidence is state the alternative and the null hypotheses. So I want to make sure we got that. So that's going to be our first Khan Academy here, okay? I want to make sure you're seeing what those are. I'm going to give you about 10 minutes here. Head on over to Khan Academy. Just the first one. Just the first one. Try that out. Make sure you can identify the null and the alternative hypotheses. I'll take a look at which ones you're getting right and getting wrong. If we have some common issues, I can address those. So make sure you try it. Don't worry about getting them wrong. That's not the point. Again, if I see us all getting the same one wrong, that tells me what I got to talk about. Let's see, it's 12:52. Yeah, about 10 minutes here. All right, let's take, excuse me, take a look here. What am I seeing? All right, number one, our first pass through was sort of 50-50. We were all split on which one to do here. Is it supposed to be mu or is it supposed to be x bar? Okay, so the hypothesis test is looking at population proportions. We know what the sample is. All right, you can calculate the average or the proportion for a sample. It's small enough, you can actually do that. So there's no question about what the sample is. Does that kind of make sense? Yeah, we never do a confidence interval for a sample or a hypothesis test on a sample because we know what a sample mean or a sample proportion will be definitively. What we don't know definitively is what the population proportion or population average is, because we can't ask a population oftentimes, right? We can't figure out the proportion or the average of a population. That's too hard. And so that is the thing that is being called into question, the population parameter, which is why your hypotheses are all about the population parameters, okay? So that's why you have the Greek mu, or you have just a regular p for proportion. You do not have x bar or p hat, okay, for these hypotheses tests. Let's see, 2 and 3 you had a decent amount missed. So here, the tea drinker one, we are filling in the null hypothesis, the proportion of, oh look, all tea drinkers. Again, the population proportion. The proportion of all tea drinkers at the company that prefer green tea to black tea is, all right, the claim is that it is 30%. So equal to 30 is that one. That's our null. Now, the alternative is the different one. He wants to know, is it something different? So the alternative will be not equal to 30, I think. But the null, the original belief, is that it is equal to 30. Number 3 had quite a bit as well. Ketchup company testing 500 tomatoes to see what percent of the sample is bruised. If the sample shows convincing evidence that more than 10%. So they believe on average that 10% is the amount of bruised tomatoes. So that's why the null is p equals 10%. And the thing they're finding evidence for, right? You find evidence for guilt. The thing they're finding evidence for is if it's bigger than 10%. So that's why the alternative is 10. That one's a little bit harder because it doesn't give you, hey, what's the original belief, Bolt? Right? I think that's why that one's kind of hard. You kind of have to infer it from their boundary here of 10%. They're okay with 10%. They think it's usually 10% if all goes well. If it's more, then we got issues. So that's why it goes, yeah. 4 went pretty well, it looks like. Not too bad. All right. Hopefully that clears up a few things for the null and alternative hypothesis a little bit. That is where this whole thing starts. If you want to find convincing evidence, that's where it starts. Now, this whole hypothesis testing thing is kind of complicated. It's a big process. And so we are going to take it piece by piece by piece. And so it is kind of hard to get an idea of the whole thing. All right, bear with me for a little bit. It's a complicated process, so we do need to take it piece by piece. But I guarantee you the pieces of the puzzle will fit together soon, so you can get an idea of the whole idea of a hypothesis test and finding convincing evidence. Okay? So, how do we make a judgment for the alternative hypothesis or the null hypothesis? All right, what is our evidence? How do we make a judgment? Well, that all comes down to the p-value. All right, this was also in the video, right? The p-value is the probability of a certain type of sample occurring given the null hypothesis is true. Okay, what are the chances of that type of sample happening given the null hypothesis, assuming the null hypothesis is true? And that actually is a conditional probability. One way I want you to think about a p-value right now is like this. It is the probability that your given sample, either x bar or p hat, whatever it may be, is greater than or equal to or less than or equal to a certain value. I'm just going to pick one. All right, what are the chances that a sample, all right, x bar sample, that a sample mean is less than or equal to a certain value, given the null hypothesis is true? Now, if that value is very low, that means the observed result is unlikely to occur by chance alone. Whoa, how did that happen? Right? That's never should have happened if the null was true. Well, if that's the case, if that's your reaction, you have convincing evidence to reject the null. If your sample is so mind-blowingly rare that it was so unlikely to occur by chance alone, then you have evidence to reject the null. Now, if instead you have a high p-value, that means the observed result, or the sample result is likely to occur by chance when the null is true. Well, then you're just not surprised. Whoa, you got an average of blank? Oh, yeah, that's kind of expected. It's not very surprising at all. Well, now you have no evidence to reject the null. Okay, so a high p-value means, yeah, there was a pretty high chance of that happening. It's not surprising. You don't reject the null. Your original finding seems perfectly plausible. But if the p-value is super small, whoa, that sample's crazy rare if we believe our null. Well, now I'm not believing my null anymore. So you have evidence to reject it. Okay. Now remember the p-value, we did some of that in the video. It's the probability of a certain sample occurring. So we're going to talk about that a little bit more and see a little bit more background about the p-value and where it comes from. All right, we did this some in the video, but it's worth reinforcing here right now. Okay, so we're going to do the next Khan Academy assignment. Okay, we're going to do this one together. So pull it up on your computer right now. You can follow along with me and click the answers, but you will want to have my screen up because we are going to work on them together here to talk about the p-value. So let me pull up my version of it. We should have the same numbers here. Come on, Khan Academy. There we go. Look, some people went ahead. What are you doing? I told you just to do the first one. Oh, you got this one around. It's kind of random which ones you get. This one is like exactly like the one from the video. I didn't copy Khan Academy at all. I actually didn't. I copied the book. I just have, maybe he copied the book. We both copied the same person. All right, let's see. Mr. Jensen told his class that he plays basketball frequently. He claimed that he could make 80% of his free throws. The class suspected that Mr. Jensen was actually less than an 80% free throw shooter. To test their theory, they had Mr. Jensen shoot a series of 43 throws. He made an average of 60% of them. So, to see how likely this would happen by random chance alone, the class performed a simulation. They simulated 100 samples of n equals 40 free throws, where each free throw had an 80% chance of being made. Binomial. That's the binomial. Excuse me. Whew. Caught in my throat there. They recorded the proportion of free throws made in each sample. Here are the sample proportions. Hey, it's a sampling distribution, isn't it? Essentially, it's a simulated sampling distribution. So they want to test this null hypothesis. Okay, that's the original belief. He claims 80%. He's innocent until proven guilty. Versus our alternative hypothesis that we think it might be less than 80%. So first things first, this is going to be technically what's called a one-tail test, or a one-sided test, because we think it's less than 80%. All right, we're only going to be checking less than 80%, right? Because it's less than, one-tail test. All right, based on these simulated results, what is the p-value of this test? All right, so remember, this is the probability. What is the probability of getting a sample like the one we did? So the sample that we got was 60%. We made Jensen actually go to the hoop and shoot from the free throw line, and he got 60%. How weird is that? Well, no, that's the question. How weird is that? Is it weird? Is it common? That's what the p-value is going to tell us. What is the probability that we could get a p-hat less than or equal to 60%, given the probability is actually 80%? Is that weird or is that common? Okay. Well, we're going to use the simulation here. Okay, so they made a simulation. So what are the chances of getting something less than or equal to 60 when we know in this simulation the proportion is actually 80%? It only happened once, right here. It only happened once. This is the only dot that's less than or equal to 60. So it happened one time out of, how many dots were there? They recorded 100. They did 100 simulations there, 100. So 1 out of 100. So our p-value is equal to 0.01. So that's a very low p-value. We've got quite a bit of evidence to reject Mr. Jensen's claim. We've got quite a bit of evidence to reject his claim of an 80% free throw average. All right, let's do one more, and then you got to ask me some questions, all right? One more, and you got to ask me some questions. Number 2. A factory produces ball bearings whose diameters are meant to have a mean of 3 millimeters. Suppose that the actual size are normally distributed with a mean of 3 millimeters, standard deviation of 2. All right, that sounds like a null, doesn't it? The actual sizes are normally distributed. That's going to be our null, the average of 3. The overseers, what? The overseers? What the heck? The overseers took a random sample. We just call them supervisors. I want someone to call me an overseer. Of n equals 100 to see if their mean diameter was significantly different than the target. The mean diameter of the ball bearings in the sample was 2.96. All right, so we have a little bit of evidence that it's not 3 millimeters, right? We have a little bit of evidence, but is it convincing evidence? Okay. To see how likely their sample was to occur by random chance alone, the factory overseers performed a simulation. They simulated 75 samples of n equals 100 diameters from a normal population with a mean of their, all right, binomial, right? That is a binomial distribution. They recorded the mean of the diameters in each sample. Here are the means from their 75 samples. So we got ourselves basically a sampling distribution from a population where the actual mean is 3 millimeters with that standard deviation. They want to test the null, that the average is 3 millimeters. I should get that. It's pretty rough. I don't know. I got the Rona. I don't. I'm fine. The alternate is that the mean is not 3 millimeters, where mu is the true mean diameter. What is the approximate p-value? All right, this one is a little bit different, okay? Because of a few keywords that we probably glossed over too quickly in that sentence. This is a two-tail test. All right, this time this is a two-tail test. How the heck did you know it was a two-tail test? Because they just want to know if it's different. All right, where was that part in the sentence? To see if their mean diameter was significantly different. So they don't care if it's too big or too small. Well, actually, that's what they do care about, all right? The ball bearing can't be too big and it can't be too small, which is why this is going to be a two-tail test, okay? If they're too big, that's bad. If they're too small, that's bad, all right? Goldilocks, it's got to be in the middle, okay? So this is why it's a two-tail test. We are looking for evidence that it might be too big or too small, which would give us evidence that it is not an average of 3 millimeters. So it's a slight difference in the wording, isn't it? With Jensen, we thought it was lower. So it was a one-tail test because we thought it was lower. So we were only checking lower. Now we want to know if it is different. So we have to do a two-tail test. All right, so we want to know the probability of getting a sample. These are means, x bar. So too big and too small. Well, our evidence says, hey, this gave us some evidence, right? The 2.96. But is it convincing evidence? So how crazy is it to get a sample like that? Okay, how crazy is it to get a sample like that? That's low, isn't it? Yeah, that's low. It's smaller than 3 millimeters. So we have some evidence that it might be smaller. Okay, so x bar is less than or equal to 2.96. Or, now, if we think that's too small, It's because it's too far away. All right, if it's too far away from 3, that gives us evidence that it's not 3. And we're saying 2.96 is too far away. How far away is it? Between 2.96 and 3. It's 4 pennies, right? 0.04. We have evidence that it's not 3 millimeters because this is too far away, maybe. How far away is it? 0.04. Well, if being 0.04 below is evidence, then being 0.04 above is also evidence. 3.04. Again, because I just want to know, is there evidence that it's not 3? If it's 2.96, that gives me evidence because it's far away. How far away? 0.04. And if I'm 0.04 below, I could also be 0.04 above. All right, the p-value. The p-value, what are the chances of getting a sample like this? Okay. So I think maybe if I write the sentence for the p-value, that will help. Okay. Let's write this, after we figure this out, let's write the sentence. So what is the probability of getting a sample like this? Oh, I didn't write the given statement. Given the null is true. Given the null is true, that the mean is actually 3. So how many are below 2.96? Where the heck is 2.96? 9.5, 9.7. So this must be 9.6 right here, right? So how many are below 2.96? 2. I can't remember numbers in my head. But how many are above 3.04 as well? So where's 3.04? 3.04 is right here, isn't it? So none, none, 1. So how many total? 3 out of our simulated 75. What is that? 4% chance. All right, do I have a text? I don't have a text. All right, so based off of this simulation, all right, there is a 4% chance of getting a sample All right, now what is about these samples? They were 0.04 away from 3, okay? We're looking at how far away they are from the mean, the null of 3. So from getting a sample with an average lower than 2.96, I froze. Is it still frozen? I don't think I'm frozen on my end. Oh, sorry. I'm recording this so you could come back and watch later. Or hopefully it pops up soon. So there's a 4% chance of getting a sample with an average lower than 2.96 or higher than 3.04, assuming the population average is actually, you can't see that, can you? Can I not go down? Bye, Bolt. There is a 4% chance of getting a sample with an average lower than 2.96 or higher than 3.04, assuming the population average is actually 3. So, does that give us convincing evidence? Hey, do we think it's less than 3? Well, we got 2.96, and there was only a 4% chance of getting something that far away. That's pretty small, isn't it? So that low p-value would give us pretty convincing evidence to reject the 3 millimeter average. To say, nope, I don't think the average is 3 millimeters, okay? We'd go with the alternative, not the null. All right, any other questions I can keep going with right now? Like, did I lose you somewhere? Is something not quite clicking about the p-value? So, yes, I'm not giving you the whole story yet, Michelle. That's the problem. Because this is low, that gives me convincing. The basics are, because that number is small, I have evidence to reject the original claim. If that number were big, I wouldn't have evidence to reject the null. In this case, the original claim was that the ball bearing had an average of 3 millimeters. That was the original claim. All right, the size of the ball bearings are 3 millimeters. So then they take a random, hey, are our ball bearings actually fitting within those specifications? So we take a random sample of 100 and see, hey, are our ball bearings actually fitting the 3 millimeter standard? And we got 2.96. All right, well, is that close enough that we now think, oh yeah, there's 3 millimeters, I just got a weird sample, 2.96 is close enough? Or is it, whoa, 2.96, dang, that's low. I don't think my average is 3 millimeters anymore. Which one of those is it? Okay, those are our two possibilities. To decide which one of those it is, we have to look at how rare would it be to get a sample like this when this was actually true. So the dot plot here gives us what the sample variability could look like. And then we count, essentially, how many actually were that low. I'm hoping you're getting some normal CDF vibes from that. We're essentially finding the area of that curve. Definite normal CDF vibes coming. Okay? Soon. Not quite yet, but soon. All right? So, does that help some? Now, I'm hoping the question on your head is, bull, how small is small enough? How big is big enough to reject or not reject? What's the boundary? That is the right question that you should be asking. I will tell you in a few minutes. That is called the significance level, and it depends. All right, there's different significance levels that you can pick. Okay, but again, recap, a low p-value means that that was super rare, and you now have evidence to reject the original claim. If it's large, well, yeah, there was a high probability of that happening. You're not surprised. You have no reason to reject the original claim. Okay. All right, let's do 2 more here real quick. See if we got this. Hopefully going a little faster might bring a few more things into perspective so it doesn't look quite as complicated. All right, Evie read an article that said 6% of teenagers were vegetarians, but she thinks it's higher. Oh, she thinks it's higher for students at her school. One tail. She thinks it's larger. We're going to be testing if it actually is. To test her theory, she took a random sample of 25. 20% of them were vegetarians. Whoa, that seems big. We have some evidence that it's higher for students at her school, right? Is it convincing evidence? To see how likely a sample like this was to happen by random chance alone, Evie performed a simulation. She simulated 40 samples of 25 students from a large population of 6%. All right, this is just the binomial distribution she's doing to make a simulation. She recorded the proportion of vegetarians in each sample. Here are the sample proportions. So there's our sampling distribution of what that sample variability could look like. She wants to test the null that p is equal to 6%. With the alternative that it's actually greater than 6%. All right, that's the one-tailed test where p is the true proportion. All right, based on these simulated results, what is the approximate p-value of the test? So the p-value is looking at the probability of getting a sample like this. What's the probability of getting a sample like this? So p hat is greater than or equal to 20%. All right, we think that that's so big that it might give us evidence to reject the null. What are the chances of getting something like that or bigger, given the null hypothesis that the probability is actually 6%? All right, well, in our simulation, which samples fit that description? So 20%, 1, 2, 3, right? 1, 2, 3. They had to give that to me in the problem. They said that Evie took a random sample and got 20% were vegetarians. So she thinks that her sample gives her evidence to reject that claim of 6%. All right, that was from her sample. So, is that sample crazy rare, or is it predictable? Given a population proportion of 6%. So that would be 3 out of, how many were there? Oh, 40. They said they did a simulation of 40. So what's 3 out of 40? .075? Iffy. Yeah, that's the one. That might give us evidence to reject her claim, or it might not. It depends. Okay, that p-value is not crazy low, but it's pretty low. There was a 7.5% chance that could have happened just because of sample variability by chance alone. So there's a 7.5% chance that, yeah, you could get something like that, even if her high school is no different. Even if her high school, 6% of the teenagers are vegetarians, you might still get a sample that high. So, that threshold. Let's talk about that threshold. What does that p-value have to be measured against? Okay, is that number too small? Is that number too big? How do we decide? Well, it depends. Okay, it depends. Let's talk about that, how it depends. It depends on what's called the significance level, also known as alpha. Okay, this is the boundary for the p-value. You set it at the beginning of the problem, okay? You say, hey, this is my boundary for being too crazy or predictable, okay? If it's below this boundary, then we will reject the claim. If it's above this boundary, we won't reject the original null hypothesis. But it's kind of a value you set at the beginning. So, some common ones. All right, my alphas kind of look like fishies. If you want to try to make yours look more like A's, be my guest. But make sure it's not a regular A. Don't give me one of these for alpha. All right, it's got to have a little something up here. I don't know. Growing up when I was doing math, it was always a little fish. So, alpha. Some popular alphas, 1%, 0.01, 5%, or 10%. Ooh, 10%. All right, but that number has to be set kind of at the beginning of the process when you're doing stats. Okay, the boundary has to be set, and then you make your decision whether you pass that boundary or not. You are not allowed to do your sample, look at it, get your p-value, and then be like, oh, well, with that p-value, I'm going to draw the line here. And that means I reject. Okay? That's bad stats. Because oftentimes, then you'll go into the problem being like, I need to reject the hypothesis so badly. What do I have to do to reject their claim? And then you'll draw the alpha to be whatever you need it to be to reject the claim. All right, that's BS. That's bad statistics. You ready for the second greatest statistics joke of all time? All right, when you do things like this, when you arbitrarily pick a alpha after the fact, you would then say, you are using statistics like a drunk uses a lamppost for support rather than illumination. Get it? He's drunk, using it for support rather than illumination. All right, you can't have your conclusion and make stats support your conclusion. You cannot start with the conclusion. All right, you have to draw the conclusion based off of the stats. Must use it for illumination. Okay, so that is why, yeah, that has to be picked first. You have to pick the alpha first and then make your conclusion afterwards. So, if we get a p-value So it's like the opposite of geometry. It is kind of, isn't it? They always say in geometry, prove that this angle is the same as that angle, don't they? And then you have to prove that it's so. Yeah, you're not allowed to do that in stats. If your p-value is less than the alpha, then this gives you evidence to reject the null. If your p-value is greater than alpha, you don't have convincing evidence. To reject the null. So the alpha is just the boundary. And I think that's what's really going to help us determine if we have convincing evidence or not, because you kind of have a procedure now. Hey, what boundary line am I looking for? Oh, it's bigger than that? No evidence. Oh, it's smaller than that. I have evidence. Okay? I think that's going to help a lot. So, let's take a look-see. Batteries. A company has developed a new deluxe AAA battery that is supposed to last longer than its regular AAA battery. However, these new batteries are more expensive to produce, so the company would like to be convinced that they really do last longer. Based off years of experience, the company knows that its regular AAA batteries last for 30 hours of continuous use. Whoa, that sounds like a null hypothesis to me, doesn't it? The company selects an SRS of 15 deluxe AAA batteries and uses them continuously until they are completely drained. The sample mean lifetime is X bar equals 33.93. That gives us a little bit of evidence that they last longer, doesn't it? Is it convincing evidence? Is it convincing? Well, we're going to check. A significance test is performed using these hypotheses. So we got our null, that the average is 30. Our alternative is that it's greater than 30. All right, Michelle, how do you determine the boundary? Right now, you don't have to determine it. They're going to give it to us. It's right here. I haven't gotten there yet. After the video lesson today, you will know how to determine a boundary line, okay? There's a couple of different factors to determining a boundary line. We got 10 minutes. We ain't got time for that. I get 20 minutes during the video to tell you that. It's complicated, all right? It is kind of complicated determining a significance level. There's a push and pull of two different issues. What type of error you want to... the video will take care of that question, okay? It's complicated. It's complicated. It's like a high school relationship. It's complicated. Where U is the true mean lifetime in hours, deluxe batteries. So they did the test and they got the p-value. Where the heck did the p-value come from, Bolt? They calculated it. How am I going to calculate it? You'll learn on Thursday. All right, right now we're not exactly calculating the p-values. We'll get there. I want to make sure we can interpret it. I don't want to muddy the waters by all the math. Just can we come to a conclusion? What kind of conclusion would you make at the alpha 0.05 level? So we did the math. The calculator spit out this value for us. And yes, the calculator is going to do it for you. It spits out the math, a 0.07. What the heck does that mean? Well, that value is larger than alpha, because our p-value is greater than alpha. Oh, what the heck? 5. All right, because it's greater than alpha, we fail to reject the null hypothesis. All right. Our p-value was bigger than alpha. We did not find evidence to reject the null. We failed to reject it. All right, this means we do not have convincing evidence that the true mean lifetime, I'm just copying the context right now, right? The true mean lifetime of the deluxe batteries is greater than 30 hours. Those are the two sentences I want you to be able to write right now. Okay? So the first sentence is the stats. Right? There's no context there. That's the stats. P is bigger than alpha. We fail to reject the null. All right, we do not reject the null hypothesis because time for the context. Okay? This is our context sentence. We do not have convincing evidence that the true mean lifetime of the deluxe batteries is greater than 30 hours. That's the sentence I'd like you to be able, well, those two sentences, that's what I'd like you to be able to write. Okay? Now, a few important things about that sentence. The first, see how I use the word true. I need to be very specific in my context that I'm talking about the population parameter, the population mean in this case, okay? We talked about that in our null and alternative hypothesis on the Khan Academy. We are talking about the population mean, not the sample mean. So the word true there is pretty important. And then also this phrase right here. Please get used to using that phrase right there. We fail to reject. Okay? We do not say that the average is 30. We don't say, can't believe I'm going to write this. We never say that the null is true. Kelly, you are exactly correct. She's talking about this true, I'm guessing right there, that word. We never say that the null is true. All right, cross that out. Heck no, we won't go. All right, we never say that that's true. It might be different than 30. I don't know. It might be different. We just don't have evidence of it right now. To go back to our justice and the court case analogy, when someone is in court, they are never ruled as innocent. A jury never says that person is innocent. right? We never say that. We just say they're not guilty. We don't have enough evidence to prove them guilty. They never say they're innocent. That kind of makes sense? It's the same kind of idea. In the justice system, we never say people are innocent. We say not guilty. They might be guilty. We just don't have enough evidence to prove it. Same idea here. We can never say that the null is true. Okay? We just fail to reject it. We just don't have enough evidence to reject it. That doesn't mean that it's true. And so you can get in big trouble if you say the null hypothesis is true. That's not what we're saying. We just fail to reject it. So that's kind of the wording you want to say. You either reject it or you fail to reject it. So at 52, I think that's what I want to leave you at. But these two sentences are ones I would like you to be able to model. Any questions about those two sentences? We got 3 minutes here. Any questions about where parts of those sentences came from? I know there's a lot of unknowns right now. Like, where does the p-value come from? All right, stay tuned. How do I choose an alpha level? Good question. Stay tuned. All right, we'll get there. We'll get there. We're sort of starting from the end. All right, this is your final answer. And in the next couple of days, I'm going to be filling in the pieces for how to get there. Okay? But in the end, that is going to be our final answer. Once we do all the math, all the conditions beforehand, all the calculator inputting, after all is said and done and the dust has settled, you'll have this number, and you'll have this number. And you will know what to do with them. All right, ladies and gents, I'll get your video uploaded here pretty soon. It's not quite up yet, but it will talk about type 1 and type 2 errors. That is picking an alpha. How do you pick the alpha? That will be your video. We don't do calculating p-values until Thursday. So that is coming, but you should be able to do all your homework from the online assessment after you watch the video. Have yourselves a great day, ladies and gents, a great tomorrow, and I will see you all on Thursday. Bye, everybody.
Thank you. Thank you, Mr. Bolt. Have a good day.
You too, you too. All right, participants.